Shall I
Excellent.
start? Okay.
Yeah, let me introduce you. So I would like to warmly welcome everyone to the third day of the complexity workshop. I hope you are having as much fun as I do. Today we start our morning session, Morning in Europe, with Bartek Czech from Tsinghua University in Beijing, China. And Bartek is going to tell us about, well, how complex is it to sew a state using the modular sewing kit. So Bartek, please take it away.
Okay, so thank you very much for inviting me, for giving me an opportunity to speak here. This work is based on this talk is based on my work with Bowen Chen and Zizhi Wang, who are my graduate students here in Beijing in various configurations. One paper is out, another one is in progress. And I want to start this talk about how complex it is to sew a state by asking what is a state. So a state is, depending on your background, you may find it completely obvious, or you may find it kind of novel to think about it this way, is a map that takes operators to real numbers. You take an operator and you take the trace of the operator times the density matrix to get a real number, which is the expectation value of the operator in that state. Now, if a state is a map, which sends operators to numbers, and there is some process that takes the operator to the number. And I wrote here, or I drew a cartoon of how you would start from an operator and arrive at some number. You would take some steps in your calculation. I want to think of this box as representing an algorithm which computes for you the values of the state map evaluated on the input operators. So I want to think of a state as an algorithm for taking an operator as an input and returning its expectation value as an output. And from that point of view, it would be natural to think of complexity as the number of steps that the algorithm runs. And so that's my proposal, or maybe my way of thinking, my philosophy about what complexity should be. And maybe I should have said this, the goal of this talk primarily is to, well, to get us thinking in novel ways about what complexity on the field theory side should be. Now, in this way of thinking, complexity is the number of states the algorithm runs. There is a little bit of a subtlety about, do I mean the number of steps taken given a generic input or the worst case scenario? And those subtleties maybe will be important down the line, but they will not be important for me today. Okay, so now I want to, on the next slide, I have an example of what it means to look at an algorithm, or what it is. An example of taking a state as an algorithm. So an example is tensor networks. So here I drew a tensor network evaluation of the expectation value of some operator, here written as inputs in a state. And so how would you compute the expectation value of the input operator? You would take this operator, contract it with a tensor network of the state that you have prepared, both bra and cat here. And then you would contract all indices, and the outcome would be a real number, which is the expectation value of that operator input in the state. Now, this is an algorithm whose steps are tensor contractions. If we assume that every contraction has equal complexity, this is an assumption that maybe you might be willing to make, then the complexity, being the number of steps we take, would be the number of tensors. Now, this is exactly the motivation for first proposing that complexity maybe is proportional to the volume of a space-time, because the people who made that proposal imagine that there is a tensor network filling in the space-time. And well, yes, so this could be actually a picture of a space-time in that view. So I give this example to make sure that there's nothing alarming or terribly novel about thinking of a state as an algorithm. Tensor networks are exactly just those types of algorithms. But there's a question. If I have if I exhibit the algorithm which computes the state for me, if I exhibit that algorithm in a novel way, which is not a tensor network, then how would I assign the relative complexities of the various steps? In fact, there is a question even in tensor networks. Maybe contracting different tensors should be weighed with different weights. We can't exclude that a priori. So let's just keep that point in our minds and move on. Another piece of the story, which will be important, which is definitely important, is the cutoff dependence on the state. So here I drew cartoons of the two most common proposals for holographic complexity, and both of them are infinite if I don't impose a cutoff. This is obvious in the bulk because the size of the spacetime is infinite. It is also obvious that it should be the case in the boundary because the dual CFT has infinitely many scales, and presumably the state has to be prepared over all of those scales. So it will take infinite work to prepare it. And so whenever we talk about holographic complexity or complexity in field theory, we always have to be mindful of the cutoff. So here's a question. What do we mean by the cutoff in the specific context of complexity and holography? We have various options for answering this. Maybe the TT bar deformation is what imposes the cutoff. Or maybe some notion of holographic RG, which is older than the TT bar deformation. Maybe that's the right answer. Or maybe there is some other not previously considered answer to this question. So whatever answer we attempt to give, it will make a huge impact on what the algorithm is. It will impact the inputs because different cutoff schemes will mean that I'm inputting different operators into the map. Presumably the steps of the algorithm will be affected, and maybe even the cost functions of the algorithm might be affected too. So, so cutoff dependence is one of the issues that we will have to tackle in this talk.
So Bartek, let me interrupt you. There is a question on the chat by Luca Tagliacozzo. And the question is if the locality of the operator is relevant in the context of the contractions that you mentioned in tensor networks.
I mean, I think it's relevant because I think we mean by the tensor network, we mean a picture of some computation which happens in the bulk for local physics. But because this talk is not about tensor networks, I don't want to take a stand either way. I think it was intended to be relevant, but it will not be relevant in my talk.
Well, could I ask also, hey Bartek, could I also ask a question? So if you slightly reinterpret the question and you think about the operator as the thing you plug into your state, not about the operator in a tensor network. So usually we measure in complexity, we usually say it's a number of steps, right, as a function of some input size. Is that something you'll talk about more, you know, how you specify basically the object of which you want to compute the correlation function? Or is it just sort of, maybe that there you could also say if it's local, maybe it's just the number of them, but if it's non-local, the size should maybe enter.
Oh, I see. So I will have some examples, or actually I will focus on one example, which is the complexity of the ground state of a CFT2. And in that example, I'll be looking at arbitrary multi-local correlation functions, so like endpoint functions of the CFT. So that's what I will be doing. And sure, it's a question, what kind of inputs operators we're willing to consider in general. That's the set that I will be considering in my example further down. Thanks.
So there's another question in the chat from Deepak on tensor networks also. And the question is, a tensor network contraction can be performed in more than one way. So then how would you measure the size of the algorithm?
Okay, I only brought up the tensor networks just to make the point that when I say the state is an algorithm, then this is not terribly new because we're used to it because tensor networks are algorithms in the same sense. That's the only thing I wanted to accomplish by bringing up tensor networks. So I don't want to go into a discussion of tensor networks because it's completely orthogonal to my purposes right now. Is that okay?
Let's see.
I'll continue. So the next remark I wanted to make, and then I will be done with my starting remarks and actually get to the meat of the talk. But one final remark is that I want to encourage all of us, I'm certainly encouraging myself, to think about not just the time dependence of complexity, but the sort of bare initial value of complexity. So usually, I mean, certainly the main motivation for thinking about complexity was to study time-dependent phenomena, like these various slices I have drawn here illustrate. That's what the time dependence that almost everyone actually cares most about. But I think the initial value of complexity is also important. And I say this well, maybe I'm just asking a question, or really I'm also expressing a belief that whenever a time dependence of a quantity is interesting, then the initial value of that quantity is probably also interesting. It's just my prejudice, perhaps. So with that, and I say this because I often encounter the attitude that only the time dependence of complexity is interesting. So I respectfully disagree with that point of view, and I want to explore the complexity of a state that doesn't change in time.
So, do you need to focus on specific information that is, say, universal? Or, I mean, somehow, because the cutoff dependent parts are changing with your choice of regularization, you might think they have something non-physical in them, right?
Yeah, so let's postpone that question until later after I have discussed the actual model I'm proposing, and then we'll be able to address it more directly. Okay, so the example that I want to focus on right now, that's actually the example, but mostly I would like you to just have in mind. What I will say in the following is not limited to this example, but this is an example that's very nice to keep in mind as we are hearing the talk, hopefully. So the example that I want to mostly focus on, but not exclusively, is the complexity of the ground state of a two-dimensional CFT. And I'm imagining that the theory is holographic, so that should also be the complexity of pure ADS-free at some cutoff. This is an important part of the discussion, like I said before, at some cutoff. So I drew a picture here of an equal time slice of ADS. I drew some cutoff surface here. And the philosophy that we should be applying is I want to think of this geometry as an algorithm in quotation marks for computing CFT correlation functions. And everything about this algorithm is customized for this particular cutoff. So the inputs are presumably given at the cutoff surface. Even the steps might depend on the cutoff. Yeah, so the cutoff is an important part of this picture. And then I want to make a proposal. The proposal is to write down an algorithm, to construct an algorithm, which is the state, which works primarily with modular modes of cutoff-sized regions, such as this cutoff-sized region on the boundary that I have highlighted here. So why would I want to make this proposal? So proposal is work with modular modes of cutoff-sized regions, and why? And by the way, modular modes are modes that are eigenvectors, yes, under the adjoint action of the modular Hamiltonian, like in this equation. So why that? The first answer is that almost all our understanding of bulk reconstruction relies on the modular Hamiltonian. That goes for the Rita Kayanagi proposal, for JLMS, for various other works like Tom Faulkner and Aitor Lewkowicz's work on bulk reconstruction. And I probably should be putting many other names here. The point is that this is our best handle and maybe the only reliable handle on bulk reconstruction. Modular Hamiltonians are. The second reason is subregion duality. Subregion duality gives a very specific meaning to the separation between the inside and the outside. Okay? So maybe this is one handle on how to understand the cutoff, which is yet different from other ways of thinking about the cutoff, such as the TT bar deformation. And then there's a third reason for thinking about modular modes, which is that we have a method for transporting modular modes. And this is called modular parallel transport. It was described in a paper that I co-authored with Jan de Boer and Lamprou and Dongshan Ge in a paper titled Modular Sewing Kit. So this is an explanation of the title of this talk, how to use the modular sewing kit to sew together a space-time, and how complex would that be? And I'm putting out the fact that we have this modular parallel transport, which allows us to move modular modes, suggests that maybe we can use this as the steps of the algorithm. That's one thing we can do to modular modes as we in constructing some kind of algorithm. Okay, so these are the motivational parts of the talk. I'm just going to summarize the strategy that I want to employ. I want to think of this geometry I drew here as an algorithm that computes CFT correlation functions. The algorithm should work by mapping modular modes of the first cutoff sized region A1 to the second cutoff size region A2, to the third cutoff size region A3, and so on. Presumably in doing this, we will be using modular parallel transport in some way. I will tell you details about this. This is just a sketch. And maybe one more remark is that as we look at this picture, it's useful to think of the algorithm as hopefully the best computation, but at least some computation of the correlation function that avoids using the interior, as in we are not using the modular modes of the coarser regions. So imagine that someone told you, compute a correlation function of a bunch of operators, but make sure you never use the infrared data of the CFT, only staying outside of some if you like, energy shell or scale shell. So from that point of view, the interior size, whatever complexity it turns out to be, volume, the Wheeler DeWitt patch, whatever, but roughly speaking, the interior size should be the extra steps that such an algorithm has to take in order to avoid coarser modular modes. So if you're willing to work with any modular modes, maybe the complexity would be much smaller, but because we're trying to avoid certain large scales, therefore, the algorithm we have at our disposal is less efficient, so it takes more steps, so the complexity is higher.
A question, Bartek, can you actually avoid the coarser scales for a generic correlation function?
Let's talk about it. Yeah, so that's what we can have a discussion about whether the algorithm I have exhibited accomplishes that task or not. Okay, so first a review of modular parallel transport. So here are the relevant references on it. The statement is that if I have two regions, let's say A1 and A2, there is a unique operator, or properly I should be saying a unique operator valued one form, which maps the modular Hamiltonian of the first region to the modular Hamiltonian of the second region. And the way it maps is that I take this operator valued one form, and its commutator with H mod gives me the change in H mod, which is also an operator valued differential form. And so that's this equation. There's an extra piece here, which allows for possibly H mod changing by its own zero mode. Now, its zero mode cannot be generated through a commutator, so therefore this is something that this operator valued one form, AMPT, can never accomplish, so I have to just add it by hand. If I further impose the constraint that AMPT, the operator valued one form which generates modular parallel transport, it itself contains no zero modes of H mod, then we get a unique object with these constraints. Now, this is a CFT, or really a field theory, or really a quantum mechanics construction, but in the bulk, after a code subspace projection, and with some suitable extra assumptions, which are mild, I assure you, we can think of the action of this operator valued one form as a vector field, which maps the Ryuta-Kayanagi surface of the first region to the Ryuta-Kayanagi surface of the second region. And that's what I marked here with these purple arrows. So what I want you to take away from this slide is that there is some way of constructing in the CFT an object which performs just this shift of the RT surfaces. And this is not any shift, it's a very particular unique shift. The next thing I want to say is that modular parallel transport can shift regions, but we can also use it to transport modular modes. So that's the thing that will eventually allow me to use modular parallel transport as a step in the algorithm that I want to construct. So suppose that I have some modular mode of the first modular Hamiltonian on the region A1. That's what I have here. And I want to write down a new modular mode for the region A2. And I write it in the following form. It's OK plus the commutator of the generator of the modular parallel transport plus with the starting modular mode. So with this definition of the new modular, of the new tentative modular mode, I will also write down what the second modular Hamiltonian is. That's the modular Hamiltonian of the larger interval. And that's H mod 1 plus a commutator of the H mods. There was also that zero mode piece that I had to subtract by hand. So here I'm just rewriting what AMPT is supposed to do to the modular Hamiltonians and writing down H mod 2 as on the left-hand side. So these are my equations that tell me what the new modular mode is supposed to be and what the new modular Hamiltonian definitely is. I take these equations and I plug them into, I write down their commutator, and I will discover that this object I have constructed here actually is a modular mode of the new region with a new eigenvalue. But the new eigenvalue or the new modular frequency is actually the same as the old one up to some order epsilon corrections. And the order epsilon corrections come from possibly from the zero mode piece by which the modular Hamiltonian may have changed. So again, if you didn't follow all the details of what I just said, it doesn't matter much. The important thing here is that modular parallel transport takes modular modes along as I go from one region to another. Okay.
Can I ask a question?
Yes.
This operator A that you define, there was some condition that it doesn't contain zero modes.
Mm-hmm.
Does it mean that in the bulk as a vector field, it somehow fixes the reparametrization of the Ryuta-Kanagi surface?
Oh yeah, so I just wanted to say, that's right. So it's if you started with a fixed parametrization of the first one, then it gives you a fixed parametrization of the second one. So this is a relative statement, which is that AMPT not containing zero modes means that it gives me a specific way of mapping one surface to another. So that's what's written here. Maybe I didn't read it. It has no components along the RT surface. I think that's what you're asking about, Giuseppe. Did I answer the question?
Yeah, yeah,
good.
Thanks.
Okay, so so good. So now
another question. I guess I asked you this before, so I just want to make sure. So the modular Hamiltonian that you define is the modular Hamiltonian that is for the region in complement, or it's just for the region?
Oh yeah, I haven't been careful about this here, but I certainly, for this philosophy to work, I have to be talking about the one-sided modular Hamiltonians. So in the paper about modular parallel transport, we made some comments about under what conditions we can think about this as a one-sided versus a two-sided problem. So maybe the short statement is that the construction of one-sided modular Hamiltonians in field theory is rather subtle. But if we believe that such an object exists, then we can definitely do this for the one-sided modular Hamiltonians. So yeah, okay. So good. So now consider the next one more ingredient that I will need is, imagine that there's a vielbein in the bulk. And the vielbein is not just an arbitrary vielbein. It's such that I have one component which points along the RT surface. So that's these arrows that I have drawn here. And then it has another component, which is obviously orthogonal, which points directly into the interior in the same spatial slice, okay? So that's a starting point. Imagine that I found a vielbein which happened to take these values locally around the RT surface. So now, if I think of the action of AMPT in the bulk as this vector field, and that vector field certainly doesn't preserve this vielbein configuration. So why? Maybe it's not, maybe I didn't tell you enough to say this, but the way that modular parallel transport acts for two intersecting geodesics or minimal surfaces in 2+1 dimensions is that it just rotates about their intersection point. So if I start with this point and do that rotation, I will end up with this purple vielbein, but not with the green vielbein that I would have wanted to. Does that make sense? So, so modular parallel transport by itself is not going to preserve this configuration. However,
there's a question from the chat. By vielbein, do you mean the local Lorentz frame in the bulk?
Yeah, a choice of local Lorentz frame in the bulk at each of these 3 points. I actually really just need these 2 points in this drawing. So, so good. So if we, so what I wanted to say is that this vielbein is not preserved by the action of AMPT, but it almost is, because if I just allowed myself to do this extra shift, then I would really shift this point to that point and everything would work. And so if we add an appropriate, what this is a zero mode of the modular Hamiltonian, because this is a translation along the RT surface. And just like Giuseppe was asking a moment ago, any such translation is actually a zero mode of the modular Hamiltonian. So if I allowed myself an appropriate and correctly chosen multiple of this translational zero mode here, then I would be able to construct a combined object which consists of a modular parallel transport and some zero mode, which actually shifts along this RT surface. It takes this field bind to this field bind to this field bind, and so on. And by construction, this object, when I do a path-ordered exponential of it around the cutoff surface, it will integrate to the identity. Why? Because it will take this field bind and move it over until the field bind comes back to exactly itself. Okay? So this is by construction true. And I just want to make a remark which may or may not be clarifying. When we are working in pure ADS3, this A tilde is actually a very tightly related. It is almost identical to the SL2R gauge field in the Chern-Simons description of ADS3 pure gravity. So if that helps you, you can think of this A tilde as doing the job of that SL2R gauge field. But if you're not familiar with it, you don't have to think about it that way at all. Okay. So I have constructed an object in the CFT. Well, really, I just pulled this modular mode out of a hat. So maybe I should say I posited that there is an object like this in the CFT, which just performs in the bulk a translation along the RT surface like that. And I want to say that decomposing this object into these two pieces, modular parallel transport and some zero mode piece, is very meaningful because that's what we mean by a division of a phase of a system with a changing time-dependent Hamiltonian into the modular Berry phase, or into the Berry phase and the dynamical phase. So AMPT is entirely due to the fact that the modular Hamiltonians are changing along. And then B is entirely due to some additional time translation with a fixed modular Hamiltonian or something that commutes with it. And that's what we would call a dynamical phase. So I just want to say that this division is very meaningful, and we have seen it whenever we discussed Berry phases in the past. Okay, so, and the last thing I want to do before actually telling you what the algorithm is I want to apply this A tilde that we just constructed to modular modes, essentially by going to the Heisenberg picture with respect to A tilde. So I start with some modular mode here, and then when I go here, what does it mean to go to the Heisenberg picture? It means that my state is staying fixed. In this case, the density matrix of my region is staying fixed, but actually the entire space-time is moving around me. So that's what I drew here by visibly rotating the cutoff surface. Also, this point got rotated to the side. That's what the Heisenberg picture with respect to A tilde is doing, where everything is shifted such that we can think of this surface as being unchanged, even though it now covers what was previously a different region, the next region in line. And after such a shift, the initial modular mode got transported, or it got transformed into this object. This is just conjugating it by the transformation matrix. And then I will continue shifting, so continue going to this Heisenberg picture as the regions are moving and moving and moving, and I will get always modular modes of this general type. Okay, so, and of course, by the time I come back to where I started, the operator will be unchanged because the path-ordered exponential of A tilde around the closed loop is just identity. So all we're doing is just looking at the system from various perspectives, which are, the new perspectives are chosen by the modular Hamiltonians of the UV-sized regions. And as we do it, we are scanning all of the tangent point, the points at which the entanglement wedges of these UV-sized regions are just touching the cutoff surface. Okay, so that's what we'll be doing. And now I'm ready to actually state what the algorithm is. So I will start with some, let's say that I want to compute a correlation function of these four operators. I'm going to take one of these operators as a starting point, and I will apply this A tilde and move it along. And I keep doing this just like we did on the previous slide until I meet one of the new inputs, one of the new operators one of the operators whose correlation function I'm computing. And then I will just tensor it, but tensoring operator with another operator, I can use the OP expansion in the CFT to merge them. So I will use the OP to merge the new input and possibly decompose the answer into modular modes of this new operator. And then I will keep going. And I will keep going until I have rotated all the way around the cutoff surface. When I'm just about to complete a full evolution, rather than going back to where I started, I will just pick out the identity component of these modular modes that I have generated along the way. And the statement is that identity component is exactly the correlation function of these 4 operators at this cutoff. And you might ask, why is that? And the answer is that all we have done is a bunch of OPE fusions. And you might say, no, I was also doing this A tilde, which was weird, but all A tilde was doing was just changing the SL2R frame along the way, which means that we're computing the same computation, but we're just changing how we look at the bulk of ADS along the way. But since eventually we came back to the same position that we started with, then, nothing, the fact that we were evolved by A tilde on the way didn't actually change the correctness of the computation. Okay, so this is the algorithm that I am proposing, and I claim that it satisfies the conditions that I said earlier. Now, here's maybe an example of how the algorithm works. So rather than working in global ADS like I did here, let's work in Poincaré. And imagine them again computing some 4-point function. And
sorry, Bartek, a quick question. So shall I think about the operators that you drew in HKLL terms, or what was the?
Actually,
or more like in the Ising model that say some CFT operators are realized or approximated by say Pauli matrices.
Maybe. So what I want to say is that there is no easy answer to this question, but the short answer is no, they're not HKLL operators. So let me try to, maybe I have 2 more slides, actually 3 more slides about which kind of answer this question. So I'll go on with the slides and we'll return to it. Yeah, I think that's the best way to do it. So let's say that I started with 1 operator, okay? And then what I'm supposed to do is, the algorithm tells me to do it, is that first I should move along, and here I chose a UV cutoff surface, which is just at a fixed value of Z in this standard Poincaré coordinate. So let's say I move along and I move along. Actually in the Heisenberg picture, I'm staying in place, but the whole line is shifting to the left, okay? But I drew this in this active rather than the passive picture. And then by the time I arrive here, I get this O1, which was now shifted by the A tilde. But the A tilde is supposed to just take me along the cutoff surface. So that's just a simple translation. That's what I wrote over here. So all I'm doing is computing I am dressing this O1 with these finite translations. So that gives me O1 of x1 minus x2 by the time I arrive here. And then I'm supposed to fuse it with O2 of 0 when I come to this place. And obviously this is the correct thing to do. These things are really separated by the correct amount, x1 minus x2. And now that I have this new result of fusion, I will carry on and continue translating, so continue evolving with A tilde until I come here, fuse again, and evolve again, until I have passed the last input, and then I can just pick out the identity component, and that is my, my correlation function. Now you can ask, is this consistent? And to ask is, so actually the question, in what do I mean by computing the correlation function? We should really ask, if I compute it at different cutoff surfaces, do I get consistent answers between them? And so here I have 2 slides which establish that the answer is yes. So consider 2 non-interacting cutoffs, and I'm going to choose a vielbein just like I did before on each of them. And I want to extend the choice of vielbein everywhere in between. Now I will transport, I want to say that we can also, with this newly extended vielbein, we can construct an A tilde everywhere in between and use it to transport operators from the coarser to the finer cutoff surface and vice versa. And so that's what I'm doing here. I'm taking path-ordered exponentials of A tilde that go from the finer to the coarser and vice versa to remap the operators for one cutoff surface to another. This is what RG-flow is supposed to do to operators in the CFT. Now, the single valuedness of our vielbein means that the A tilde I have constructed is flat. And because it's flat, any object that I have constructed from path-ordered exponentials of these A tildes is freely deformable. So by the time I have attached my computation on the red line through these extra RG changing or scale changing operators, by the time I have attached it to the blue line, I have computed the same object in two different ways. So a correlation function at one cutoff scale is equal to the other one up to the effect of these dressing factors, which perform our G-flow. And they are equal because the A tilde we have constructed is flat. Now, this is, roughly speaking, the language in which my students and I have, oh, it should have been plus 10, sorry. This is the language in which my students and I have described this calculation in the last paper. And there we use the Chern-Simons formulation of ADS3. But again, A tilde is very closely related to the Chern-Simons gauge field if we are talking about pure ADS3. However, I want to emphasize that everything I said seems to work generally and not just in pure ADS3. So what do I need? I just need some way of pushing over this field bind from this point to that point. And I already have a construction of modular parallel transport in any background, not just in pure ADS3. I further posit that there is some zero mode which is going to translate me from this point on the RT surface to that point of the RT surface. And then A tilde is just a combination of these two things. Once I have constructed such an A tilde, I can go from a choice of field bind which is tangent to my cutoff surface to the A tilde, and then go through the algorithm like I described it before, and I will be computing correlation functions in an arbitrary state. And so it seems that this A tilde allows me to formulate the algorithm more generally, assuming that I know how to write down the B and the AMPT explicitly, which is a very hard thing to do, of course. So hopefully I have...
There's a question on the chat from Claire Zukowski. Can you explain more what you mean by having A tilde very closely related to the Chern-Simons connection? And what changes when you move beyond the pure ADS case?
Yeah. Oh, so when I move away from pure ADS. Oh, okay. So maybe I should say this. This AMPT, if I'm in pure ADS, happens to be valued in the isometries of ADS, and the isometries of ADS live in SL2R. So this operator valued one form is an SL2R gauge field by construction. But if I am not in pure ADS, then these AMPTs are not in SL2R, and so they are not SL2R gauge fields. And that's just fine because there is no SL2R description of non-pure ADS3 geometries. So that's the reason why I have this very specific correspondence in just that particular case, but not elsewhere. And also there's one more subtlety, which is that there are two fields, A and A bar, in the Chern-Simons formulation, and one of them is sort of twisted by an inversion relative to the other one for reasons that have to do with the CPT invariance of the CFT. So this A tilde doesn't have that feature. So you have to do a little bit of a song and dance to go from the Chern-Simons language to this A tilde. Okay.
I have a question.
Yes.
So is it correct to say that in a general background, this A tilde is just a gravitational connection which is compatible with the metric, the VL bind?
Almost. The reason why I say almost is that this is a connection which is designed to map surfaces to surfaces. And so one of the claims in my paper with Jan de Boer and Lampros and Dongshan Ge is that when you compute holonomies of this AMPT, then it's really the same as computing the holonomies of the Riemann curvature, except that you're doing it surface by surface. So what you're getting is a sort of X-ray transformed or integral transformed version of the usual holonomies. So the answer to your question is yes, except for the fact that we're not moving points, we're moving surfaces.
Okay.
Okay. So, and by the way, the fact that we're moving surface and points is very important because I'm supposed to be working with whole H mods, which are features of regions, not features of points. So that's why I need an ingredient of this type. Okay.
Bartek,
so
I have a question. So the procedure you describe, it seems to me that it's a CFT prescription, so it should work in any 2D CFT. Of course, you have a lot of bulk pictures along the way, but the prescription you told us seems to work for any CFT. So could you say you wanted to compute this 4-point function here? Where did you really use any input that there's a bulk?
In pure ADS3, nowhere. And the reason why I shouldn't be using it anywhere is that the geometry of ADS is just a feature of the group theory of SL2R. You can derive everything from symmetries. So any CFT tool will work the same way for any CFT tool. So the true test of holography will be, or like the true place where we'll decide whether this story is holographic or not, is when we study states which are not pure ADS. And we have in our paper a construction, well, a set of equations that you would have to solve. So an implicit construction of what this AMPT is in any state. I'm not aware of an explicit construction of B in states which are not pure ADS. But let's imagine that there was such a construction. Then we would have an A tilde and everything would go through. But this AMPT in states other than the vacuum is going to be very different from theory to theory. And B, no one even wrote it down, so that's also going to be different from theory to theory in non-vacuum states. They just happen to be fixed in the vacuum.
Right,
but answer your question?
Sorry, if you can do 4-point functions, I'm allowed to interpret that 4-point function as a 2-point function in a new state. Say 2 of the operators are the same.
Yes.
So in some sense, if you can do arbitrary point correlation functions, I would say you're very close to being able to do it in any state. I mean, you may not be able to do topology and that kind of stuff, but
the thing that the place where we would be using this is, okay, so if I want to recast it as a calculation in a non-trivial background of a 2-point function, then this would be a different algorithm. Why? Because I would have to construct the algorithm from scratch, because I would have to construct the state which is created by 2 of these operators and write down the modular Hamiltonians for all the regions in the O. Then I would have to say, in that state, what is my cutoff surface? And once I have a cutoff surface, I would have some regions which have some modular Hamiltonians, and I would have to reconstruct AMPT again. So basically what I want to say is that if you reinterpret the same calculation as a new calculation in a different background, well, the complexity story tells you that you should be, we hope that the answer to what complexity is geometric. You change the geometry, you use these 2 operators to sort of back react, and the modular Hamiltonians have changed, the story has changed, the modular parallel transport has changed, you have to have a do-over. So the short answer is that we can just go ahead and interpret this in 2 different ways.
Thanks.
Okay, so because the title, I know it's been 40 minutes, but I got a lot of questions, so hopefully I get to finish the talk.
Sure, if you can wrap up between 5 and 10 minutes, that would be great.
Yeah, 5 and 10 minutes will be enough. So,
Bartek, can I ask a question?
Yeah.
Just quick. So if you're not in empty ADS, then we don't know how to construct these edge modes microscopically, right, in generic state.
That's correct.
So that means that if you don't have a bulk dual, that you don't really have access to B microscopically in the theory. And also, I think it's very hard in a generic state to actually localize an operator on a specific point on the minimal surface. Because if you don't have these exact edge modes that move you along the minimal surface, you can also not do a Fourier transform with those operators. So isn't that a problem if you want to do this in a generic background?
That's a problem if I want to do it in a generic background, or that's a problem if I want to do it in a non-holographic theory?
Well, in the generic, if you have a holographic dual, then you think there's an approximate large N description of these edge modes. But if you have an abstract CFT, then you probably
good. So Jan, you're answering Alex's question and saying that in holographic theories this has a chance of working, but in non-holographic theories probably this equation is not well defined. Is that what you're saying?
That's what I'm thinking. Yeah.
Okay, great. So excellent. Well, thank you for supplying this answer. I definitely intend for this to be a holographic story. So thank you very much for this. Okay, so the title was.
Sorry, can I? The question also, Jan's question also included a comment about backgrounds, other backgrounds. can you disentangle the difference between whether this works in non-holographic CFTs versus holographic CFTs with different backgrounds?
So I think that in holographic CFTs in different backgrounds, the story should work. And the only obstacle that I see is that I haven't seen any construction of this B object from the CFT point of view. But I think it should exist. That's really the short answer. Whereas in non-holographic theories, the B is not even well defined, was Jan's point, and I agree with it.
Okay, thank you.
Okay, so so the title was How Complex is the Algorithm? And I want to make a point about complexity. That's really the point of doing this exercise. So I want to, let's inspect what the algorithm does and decide which parts of it are hard and which ones are easy. So let's say that I started with some modular modes and I apply first, so I have this AMPT plus B. First I apply AMPT. What this does is rotates the RT surface to a new RT surface. This is done through that commutator. The next thing is the zero mode. But because the zero mode is a zero mode, it doesn't actually change the operator. The worst it can do is just rescale it by some factor, which is related by how much of a B I have. Okay? So I say that this step is easy. We also, if I happen to meet a new input on the way in the algorithm, like this O prime, then I have to fuse it with what I was carrying from before and decompose the rest into modular modes. And I think that these steps are also easy. We can have a discussion about why I think that it's easy, but please just bear with me for now. I'm almost out of time, and let's just go along with the assumption these steps are easy. The point I want to make is that the truly hard one is this one. And so I'm going to assume that this is the driver of the complexity cost of the algorithm. And so here I have a little bit of a cryptic remark. I will explain it later, that this cost is actually context dependent, which is something that's absent from all other formalisms for talking about complexity that I have seen. But please remind me, if I don't say anything about it, then please remind me to say so. So I am going to assume that this is the driver of the complexity cost of this algorithm. So now let's focus on ADS-free and see how this works. All instances of modular parallel transport, if I'm in pure ADS-free, not in general, are global conformal transformations in the same elliptic conjugacy class of SL2R, which is maybe a fancy way of saying that they're just rotations about bulk points. Because they are all rotations, they're all in the same conjugacy class, it is meaningful to assign a relative magnitude to them. And the magnitude is just the angle by which I am rotating. Now, if they were not in the same conjugacy class, this is the content of this warning part, then we wouldn't know how to say, oh, here I'm doing one kind of modular parallel transport, but here a different operator is affecting modular parallel transport. They are not really because they're not in the same conjugacy class, I have to make a decision which one is more costly than another a priori. But in this case, I don't have to make an arbitrary cost assignment because they are all related by conjugation. And so we can say that the cost is just going to be proportional to the angle of rotation in the bulk. And if I say this, then this leads me to the conclusion that complexity, an infinitesimal increase in complexity at one step, is proportional to this quantity along the cutoff surface. K is the extrinsic curvature. That's just what these rotations are doing. They are computing the extrinsic curvature of this cutoff surface. And if I buy into this conclusion, again, this is specific to ADS-free, not to other states, then complexity ends up being the integral of KDS, which is R times volume plus 2 pi. And so I have reproduced the volume proposal in that geometry. But like we said, in other geometries or in other states of holographic theories, it wouldn't be this answer. Okay, so I want to just, if I have 1 or 2 minutes, I want to draw an informative contrast between two different cutoff surfaces, which will hopefully illustrate more the features of the proposal I'm making. The reason why this extremely small cutoff surface, which is basically just a point in ADS, it's a very sick cutoff, but bear with me, and a more realistic cutoff, which is a rotation invariant cutoff someplace far away from the center. The reason why contrasting these two things is worthwhile is that A tilde is actually the same thing. In both cases, this is rotation about the center. So, but obviously this cutoff surface and this cutoff surface have very different complexities as I computed them and as we expect on general grounds from other sources. So what gives? And the answer is A tilde might be the same, but the decomposition of A tilde into A plus B is different. In this case, we are constructing A tilde through very big modular parallel transport rotations, followed by pretty big translations along the geodesics. Whereas here, all I'm doing is just a single rotation, flip and done. So it's much harder to affect the same global rotation if you happen to be working near the boundary. And that's the reason why I said that the cost is context dependent. Same A tilde, but different costs. The other thing I wanted to say is that in this case, complexity is just 2 pi. So I would call this algorithm an oracle. Why? Because it just has to do a 2 pi rotation to scan all the inputs. The moment it has the inputs, it already spits out the outputs. So it's like a table of all possible correlation functions. Whereas in here, I actually have to do some computation. And the reason why I'm doing this computation is that I'm trying to move only the modular modes of these small regions. And only working with those, but not working with the largest scales in the field theory, makes me incur a cost, which is just the volume. So the volume is the complexity cost of not using the large scales in the CFT. That's something I advertised before, but I think we can see it from this slide. And so this is the last slide I have. I have some salient features of the proposal, and I have some comments and questions. Maybe I will stop talking and you can just read the comments. Thank you very much.
Hey, super, Bartek, thanks. Let's unmute ourselves and let's do bravo for Bartek. Excellent. We had quite a bit of questions, and we still have time to ask a few, if there are some. And then after Hosse's talk, there's going to be still about 10 or 15 minutes Bartek's time to ask further questions. So does anybody have a question now?
I have one.
Sorry.
Oh, go ahead.
Okay, so my question is that all of this is based on being able to define a modular Hamiltonian, right?
Yes. Yeah.
So one should be able to, do so for a density matrix for any state in any background, no?
Yeah, so like we said, I think Jan said it better than I, that the construction of this B object was not, is really relies on holography. And I also, even before that, first of all, the starting point was some bulk cutoff curve. In a non-holographic theory, what do I mean by that? You might say, I have some, I just have a bunch of like cutoff sized regions on the boundary. But then it will not tell me what the B's should be in general. So in a non-holographic theory. So if that's the question, then the answer is the B relies on holography. And even the cutoff surface relies on holography.
Thank you.
Was another question in the audience?
Yeah, can I ask? So in the case where you take the point-like cutoff, if I understood correctly, this complexity is fixed because you are ignoring all the other costs that you say were easy steps, right? But in this case, they might be the predominant part of the complexity.
Yeah, maybe a better argument. That's true. So maybe a better reason for like associating this step with the complexity cost is not that these steps are easy, but I expect that I will have to do these steps every time I performed a little bit of a rotation. And so maybe we should factor in the cost of these steps into the cost of the rotation. Maybe this is a better answer to why. Anyway, but yes, everything you said is correct. I have ignored those costs at this point. But maybe not ignored, maybe I just incorporated them into a larger combined operation, which is modular parallel transport plus diffusion.
But so the complexity would be fixed anyway? Is that your answer?
Yeah, I mean, I'm trying to define a model that could be more general than that works for an ADS3 as I understand it, but is written in a language that doesn't make a commitment to ADS3. So the ADS3 story was written in the previous paper that's already out, and I want to reformulate it in a language that doesn't rely on the Chen-Simons formulation. And so, so yeah, I mean, I have just, in these considerations, I have ignored the cost of making larger, how do I say this, of making modular modes out of tensor products of modular modes, if that makes sense. I have sort of ignored the cost of that. That's true.
Okay, I see. Thank you.
Now, there is a question here, though. If we expect that the answer to what holography is geometric, sorry, not holography. If we expect a geometric answer to what complexity is in holographic duality, that's what I meant to say. If we expect that complexity has a geometric dual in the bulk, then do we think that some feature of the bulk geometry reflects like the difficulty of how hard it is to some properties of the matrix of OPE coefficients? I probably wouldn't, but maybe.
Hi, Bartek. Can I ask a question?
Sure.
Hi. So yeah, actually, maybe you mentioned some words, but I understood that these connections or these Wilson lines, they move you to the bulk in some way, and you said that you think about them as in some kind of relation to TT bar operator.
Oh, I don't think of them as in relation to TT bar, and I don't know if a priori these languages, at least at first sight, look extremely different. Because
okay,
in one case,
elaborate what do you mean by you mentioned something about the TT bar that is moving.
Oh, I just meant it was TT bar was a straw man here. I was just saying we have to decide what the cutoff is. Maybe it's TT bar, maybe it's something else. And then I just went on to saying, but I'm going to do something very different. So there was no relation to TT bar.
Okay, thanks for clarifying.
So I also have a question. So do you understand this factor of additional 2 pi when you use the Gauss-Bonnet?
This part here is meant to be an explanation of it. So what I do is like I start the calculation when this is my region, and I just have to rotate the region so that whatever inputs I have, I will just read them off. And as I read them off, after I read them off, I automatically give an answer without any further computation. So the 2 pi is the cost of making a full rotation so that we look at all the inputs. And I think the more meaningful question is about how much extra work did I have to do because I was at a finer scale. And that's what the volume is.
And do you have some ideas how it can work in higher number of dimensions? Or it's very specific?
That's one of the questions that I have here. So here, the algorithm was, I think here, yes. So the algorithm works by scanning the cutoff curve. And in 2+1 dimensions, the cutoff curve is 1-dimensional. So I just have a single 1 form, and I just have to use it to parallel transport along the curve. Well, in higher dimensions, I would have to have some kind of 2 form. And I'm not aware of a construction of such a 2 form. So maybe the algorithm should be completely reformulated, or maybe I should try to construct a 2 form valued operator, or maybe there are all kinds of potential possibilities, none of them particularly well motivated. But yeah, as I have introduced the algorithm, it only really works in 2+1 dimensions currently.
Any last on record question for Bartek?
Yeah, maybe I can ask one. There's something a bit counterintuitive for me in terms of what a cutoff really is. It seems that in your story, you're picking a cutoff and then you're saying, let's only do transformations at that cutoff scale. Is that the right picture, or?
Yes. And So good. So you might say, what is the role of the bulk? Yes, and that really goes to the core of the title of the talk. So I tried to say it here with the comment. So the bulk is an algorithm. That's not really true. There is an algorithm for every cutoff surface, as I have said it. Yeah? So imagine a foliation of space, a radial foliation by a bunch of cutoff curves which are non-intersecting, one inside another. So then you can ask, how do I relate one algorithm to another? And somehow relating one algorithm to another should allow me to use more tools. As in, like, I can go to coarser scales, so the algorithm gets more efficient. So I'm using less volume in the middle. So this suggests that maybe we can write down a differential equation, which is change in volume or change in whatever complexity is holographically equals how much easier the algorithm was when I relaxed some restriction, which changed the cutoff curve. So this is the content of this question here. So I think it's not counterintuitive the way we're saying it. It's not like I have actually derived complexity by this procedure, but the fact that we're doing it locally at the cutoff surface at least opens that possibility that maybe we can set up a differential equation for what complexity should be, and thereby actually prove some version of the conjectures.
Right, but somehow the volume.
Sorry. Let's perhaps return to this after the second talk and take 5 minutes break. So that Jose can share his slides, and we'll take a bit of break.
Yeah, and I will leave the salient features slide so that people can formulate questions.
Yeah, so thank you, Bartek, and let's resume in 5 minutes, 10:10 in Europe.